So thanks for joining me on the lecture 5.4.2 regarding the Kronig Penney model, and of course the course is solid state physics. So what we will do here on this lecture is that we will solve the Schrödinger equation, and of course we will solve that for a single electron in a periodic potential, and now we have a specific shape for the potential, so we will consider a square periodic potential. And for completeness and for educational purposes, we will first solve the equation in real space, and later on we will solve it in the so-called reciprocal space. So essentially we will be using the central equation that we derived in the previous lecture. And let me spoil you already. What we will learn is that now, after having a nearly free electron in our system, we will have essentially band gaps forming in our dispersion relation. So that we will have in our modified system. Now that we don't have anymore just free electrons, but rather nearly free electrons. And we will verify both approaches, and we will show that we will end up with equivalent results, and conclude by speaking of the implications that we have with what we discover for the band structure in general. So quite a bit of things that we will be covering. So let's then just get started as it is. So the Kronig Penney model essentially is a nearly free electron model where we are treating a periodic square well potential. So the square well looks like this. So we have many different parameters that they describe it. And then the potential will be, and for simplicity, we're just treating a one-dimensional system here. So our potential depends on the x-coordinate and is of the form that, of course, it will be lattice periodic. So that the potential in the position of x must be equal to the potential in the position of x plus capital R, where R is the Bravais lattice vector. And the shape of the potential is such that we have a height of the well that's denoted with the U0. We have A, the width of the well, and then we have B, which is the width of the potential barrier as shown in the figure. And nice thing about this model that it's analytically solvable, and of course it does give already rise to band gaps. So that's nice because it does elucidate us a little bit more about the electron or energy band structure that we want to understand in our treatment of solids. So what we will do is that we will first solve this Kronig Penney model into real space. So essentially we will be solving the below Schrödinger equation, and please remember the Schrödinger equation in 1D. We don't need to have the Laplace operator, we can just have the second derivative with respect to the variable x, and then we have the periodic potential ux, and then we have the psi, and this equals to the energy of our electron, the state, and then we have the psi, the electron wave function. And after that, we will solve the problem in the reciprocal space, so in the so-called K space or in the momentum space using the central equation. And we will verify that both of the approaches work so that we get the same kind of solutions out. And then we will note that if we would want to generalize things further, of course, into a more complicated shapes of potentials, this approach would give us nice tools. This approach based on the central equation, because then we can describe a more arbitrary potential using the Fourier series description, and then we would have tools already to solve it using the approach we outline here. So earlier, when we have encountered non-periodic square well potentials, like we have found specific types of solutions already, and we know now that we should try to seek solutions that are somehow similar, so that there will be parts of the solutions where we want to know how they look like inside the well, and then these will be of the form, these parts inside the well, that the wave function there, the psi, will be of a form that we have A is some constant to be determined times exponent ikx, and then capital K now denotes the wave vector inside the wave well. And then we have also a possibility that the wave function propagates in the other direction, and that's associated with the constant b times exponent minus ikx. So a plane wave propagating now a different direction. So these A's and B's are plane wave amplitudes that we want to be determining later, and they are constants that essentially the solution is a plane wave. K, capital 1, is the wave vector, and that is related to the energy eigenstate by a known formula. So we have E times h bar squared times k squared divided by 2m. And now we have the other form for the solution, so that essentially the electron can also be inside the barrier. So mathematically speaking, and then the small x must be between 0 and minus b when we are in the first Brillouin zone. And there the solution will be of a form that we have a c times exponent qx plus d times exponent minus qx. So here again, c and d are constants that we want to determine later, and g is the imaginary part of the wave vector. So we have essentially a decaying wave, exponentially decaying wave, or exponentially amplifying wave inside the barrier zone. That's the generic or general form for a solution. And what we must do next is that we now must generalize this generic non-zero potential into a periodic system. So we must impose a periodic boundary conditions for the system. And that we can do by just denoting that the psi between a, where the x is between a and a plus b, that must be equal to the psi where x is between minus b and 0 times exponent ika plus b. So here, of course, we are taking use of the Bloch function, and k is the wave vector of the associated Bloch function. So this is now the kind of what we know based on the Bloch theorem, but we have a solution and it must be complying with the lattice periodicity, and we know roughly already the formula, how it must look like. And now we have the insanely complicated looking set of equations that we have actually many variables. So we have the a, b, c, d's, we have the q, we have the k, and we need to somehow find a solution psi and the second derivatives in order to find solution for the Schrödinger equation. And how do we do that? Of course, the solution, we know that it must be the wave function, it must be continuous, and so this then gives us further equations that we can use to solve how the a's and b's and c's and d's look like. So at the position of x equals 0, this condition that the wave functions psi and their second derivatives, they must be continuous. This gives us two equations. So first of all, that gives us a restriction for a's and b's and c's and d's, so that a plus b must be equal to c plus d. And then the second one, when we are looking at the derivatives, we get that the minus k times a minus b must be equal to q times c minus d. And when we go to a position where x equals a, then we have further restrictions, further equations, so that the exponent ika times a plus b times exponent minus ka must be equal to c times exponent minus qb plus d times exponent qb, and this multiplying exponent ik a plus b. And then the second equation follows by restricting or requiring that second derivatives in position if x equals a must be also continuous. So we further have a further restriction. So ik times a minus exponent ika minus be minus ika, this must be equal to q times c minus e minus qb minus d exponent qb times exponent ikab. Two long equations to speak out loud. So now we really have a linear system of equations, maybe you already noticed, and then we must look into the solutions. And we can form a matrix equation, and then we can note that this kind of matrix equation basically has a unique solution only when the determinant of this coefficient matrix that we form vanishes. And I won't show the math, but I think Kittel was saying that it's a little bit complicated, or not complicated, but just long, and that's, I will believe, Charles Kittle when the person is writing in his book, which is a little bit mathematical, that this is not straightforward. So after like a tour de force in algebra, we found, or somebody finds, the solution will be of a form that we have q squared minus k squared divided by 2 times qk. Then we have the hyperbolic sine of a qb times normal sine of ka, plus hyperbolic cosine of q times b times cosine of ka. And then on the right hand side we have cosine of small k times a plus b. And this, of course, looks very bad. Mark Stockman, like Igal Brenner would say that this is impenetrable equation, but nevertheless, like, it's not that bad, and certainly computers can plot it. So basically, like, it's not that bad. And we will limit our treatment to thin and infinitely high potential barriers so that we can further simplify this equation and we can actually more easily plot it, how it looks like. But this is our dispersion relation. So this is important. We want to look into it a little bit more. So we further simplify, we say that the B equals 0 and then the U naught equals infinite. So essentially it's a thin, infinitely high potential barrier, and that will simplify the math. And now we can further define that we have, let's take a quantity P that is equal to Q squared times BA divided by 2. And these together results in conditions that the Q is far larger than K, and then Q times B is far larger than unity. And now we get the dispersion relation in a quite understandable form, so that we have P divided by Ka divided by sines of Ka plus cosine of Ka. And this is equal to cosine of Ka plus B. So now this is actually not that bad anymore. So like a normal cosines and sines, and this looks like something that I can actually plot. And this is what I will do later on in this slide. So I have my dispersion relation for a nearly free electron in a periodic square potential. And the wave vector k is related to the energy as usual. So E equals h bar squared times k squared divided by 2m. And now like I can plot the equation. So the equation, and this is really a dispersion relation for our electron, can be plotted, and for some choice I'm just plotting these for a value of b equals 3 times pi over 2. So this is how it looks like, our dispersion relation, when we are plotting it as a function of k, a, and in the y-axis we have the energies. And this equation, of course, this dispersion relation, it's a so-called transcendental equation, so that we cannot really solve the term into a form that we have a k, all k's in the other side. So we just need to come up with the different ways of actually plotting it. So you can have, for example, numerically plot things, but you cannot just form a normal looking equation of that. But nevertheless, like, computers can plot like even more like complicated equations, so it's not that bad after all. And the main thing here, what we have is that we will first of all have unfolded description as our A figure. Then in the B and C figures we have folded descriptions of the dispersion relation, and essentially they are now folded for the first Brillouin zone here. So essentially I'm having the first Brillouin zone from minus pi to pi, and here I have my bands, and interestingly some empty space occurs, and then the bands continue here, and then again I have an empty space here, and then I have further on bands. There's symmetry here with respect to origo, so I can really just simplify things. I can just plot what happens from origo to pi, and this is so-called like a folded first Brillouin zone. Or then I can also just plot all the Brillouin zones using a so-called unfolded description. So this is how it then would look like. But in all the cases, no matter of like how I describe this function, how I plot it, there will be these kind of discontinuities of the function when we are having nearby the Brillouin zone. So there will be a kind of like a shift in the energies. And these essentially are our band gaps. And now in the free electron model, we did not have any band gaps in our dispersion relation. So this is really arising from the fact that we are now having a periodic potential in our Schrödinger equation. And this is quite important when we want to understand the electrical properties of solids and also the other properties, that this concept of a band gap, because that really means that we don't have an electron state inside the band gap. So we cannot really, for example, lift up an electron into the band gap. And this is really something that then distinguishes metals, for example, from semiconductors and semiconductors from dielectrics. So this is a very important concept to remember. And it's really important to know where it arises from in the mathematical description. So it arises from the fact that we have a non-zero periodic potential. And that's what we wanted to say here in the first part for the Kronig Penney model. So maybe I should stop here this lecture and repeat like the derivation, like finding a solution for the Kronig Penney model in the reciprocal space as a second follow-up lecture, so that maybe it's easier for you to, instead of a single long lecture, actually go through 2 smaller lectures. So thanks, and bear with me for the next part, where we will be continuing to look into the Kronig Penney model. So thanks and bye-bye.